In this video, we will discuss aromatic molecules, which, contrary to perhaps what you might assume from this name, they do not necessarily have to be molecules that have a strong smell. The name aromatic did originate because the first examples of these types of molecules did have a strong odor, but since that time, a wide variety of molecules that fit the definition of aromatic compounds do not actually have a strong odor. So by the end of this video, we will be able to recognize what an aromatic compound is. We'll learn some key features of aromatic molecules, and we will also learn about what impact certain aromatic molecules may have on DNA and health. Stay tuned for that. The simplest aromatic molecule is called benzene. Benzene has 6 carbon atoms in a ring, so I'm drawing this hexagon shape here, where each bend in the line represents a carbon atom. In the structure of benzene, there's an alternating pattern of double bond, single bond, double bond, single bond, like so, giving a system that is so-called fully conjugated all the way around the ring, where conjugation or a conjugated system refers to the pattern of having double bond, single bond, double bond, single bond, double bond, and so forth within a system. And in this case, the system is all contained within a ring. Now, keep in mind with benzene, we could also draw that line angle formula a second way, which is to have the hexagon like we had before, but instead of having the double bonds in blue here, here, and here, we can move those over by one spot to put them here, here, and here instead, such as I will draw out here. So double bond here, and double bond here. You'll notice that all the double bonds just moved by one position toward the right and going from the structure on the left to this structure. Now, in actuality, due to the electron arrangement here in the conjugation, the electrons actually migrate throughout this entire system through a phenomenon called resonance. We won't get into resonance in depth in this video, but due to the fact that the electrons can be represented equally well like this or like this, there's a third common abbreviation for benzene, which is simply to draw a hexagon like so with a circle inside. And that's our universal symbol for the fact that we have that conjugation going on within the ring where there's double bond, double bond, all the way around. So be aware that when you are looking at benzene drawn out, you may see the pi bonds shown like so, or you may simply see it drawn as a hexagon with a circle inside. And if you see that symbol, hexagon with a circle inside, you need to be able to recognize that what that actually refers to is this conjugated system within that 6-membered ring. We could also draw this out as a condensed structural formula instead of a line angle formula by drawing 6 carbon atoms in a ring, such as I'm doing here, making my hexagon, spacing out the bonds as far apart from one another as possible in that hexagon, and then in that condensed structural formula, drawing out my carbon-carbon double bond, single bond, single bond pattern, like so. And if we fully add all of the hydrogens necessary to fill the octet on all of those carbon atoms, which we are always aiming to fill the octet when we're looking at structures that we can actually work with and that we'll be looking at, we would see that the formula of this molecule is going to amount to C6H6. 6 carbons, 6 hydrogens, because at each carbon there is exactly 1 hydrogen scattered around this ring system. Now, benzene is one example of an aromatic molecule, but it's not the only example. But what we are going to see for our intents and purposes is that the aromatic molecules we will be dealing with are all going to feature this theme of having a benzene ring and then perhaps some branches coming off of that ring to transform benzene into a molecule that would have a different name. Benzene is the IUPAC name for just 6 carbon atoms with alternating single bond, double bond around them, and no branches coming off of it. Once branches are coming off, we will need to come up with a more complex name that accurately reflects the identity of those branches. Now, when we are talking with regard to aromatic compounds, A term that may also come up in these discussions is arene, A-R-E-N-E. And arene is synonymous with aromatic compound. So at the heading of this slide, rather than saying aromatic molecules 101, I could have instead said arenes 101, but I wanted to get this aromatic compound terminology out of the way first. When we look at aromatic compounds in general, what we'll observe is that all of the carbon atoms of the ring are all going to be trigonal planar, in other words, flat. The reason why they are all flat is because you'll notice that each and every one of these carbon atoms is part of an alkene group. And so the entire shape here of this molecule as a whole is going to be trigonal planar because every single one of those carbon atoms is trigonal planar, meaning that the bond angles throughout here, where I'm putting these green symbols, is 120 degrees at whichever carbon atom of that ring you were to pick. Now, this fact that aromatic molecules lay planar relative to the aromatic group has important implications. For example, with regard to health. Looking at the structure of DNA, DNA is a double helix. In that double helix representation, where this is one of the helices I'm following with my laser pointer, and then here's the other following the other line through, what we see is that the nucleotides, the building blocks of our DNA, sit planar here, 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 and here. And the planar aspect of this is due to the hydrogen bonding that occurs between the two strands of DNA. That helps hold the two strands together and is essential for the function of the DNA. Now, due to the fact that these lay planar or flat, what can happen with certain aromatic molecules, which are also flat, is those aromatic molecules can intercalate or wedge themselves within the DNA double helix. And in this schematic, this feature here that I've circled in red represents an aromatic molecule that we're illustrating. This red or burgundy aromatic molecule has intercalated or wedged itself in to the DNA double helix, resulting in damage to the DNA, and that can trigger a variety of diseases such as cancers and other maladies that come from DNA mutation. So the phenomenon where the DNA can be damaged by a planar structure wedging itself within that DNA is referred to as intercalation. So intercalate, or an intercalator, is a chemical, generally a planar compound, a planar molecule such as these aromatic molecules, that disrupts the structure of DNA by wedging within it. And this is one reason why a variety of aromatic compounds, not all of them, but a variety of them, are known to be cancer-causing agents. This is certainly not true across the board, but one example is the case of polyaromatic hydrocarbons, or PAHs, standing for poly meaning many, aromatic compounds or hydrocarbons. Remembering from earlier lessons that hydrocarbon refers to molecules that have just carbons and hydrogens. Polyaromatic hydrocarbons are carcinogens, cancer-causing agents. They are relatively strong intercalators in many cases, wedging into DNA, and the term polyaromatic hydrocarbon we can dissect to mean many aromatic molecules that are fused together. And the way this generally happens in terms of how things are fused together is you have a bunch of aromatic molecules that link together like so. And not all of these polyaromatic hydrocarbons are carcinogens, but a variety of them are in fact carcinogenic. So we have aromatic ring here connected to another. connected to another, and you'll notice that there's a system of complete conjugation throughout the molecules where all of these carbon atoms are part of alkene groups. We have a pattern of double bond, single bond, double bond, no matter how you slice it through the molecule. And that is going to result in the structures being planar as a whole. These polyaromatic hydrocarbons are very prominent in burnt meat. That is why it's encouraged that folks limit their consumption of things cooked on the grill, as delicious as some of us might think they are. They're also known to be laced with these polyaromatic hydrocarbons. Also, cigarette smoke is rich in polyaromatic hydrocarbons, as well as a variety of other products of combustion or products of burning. And due to the fact that these are, many of them are able to intercalate DNA, that contributes toward their negative effects on health. Aromatic groups are very common within complex molecules. Not only do some aromatic molecules act as intercalators, which is generally considered to be a negative feature, but aromatic groups are also common in drug molecules, such as an example here, the anti-anxiety drug Klonopin or clonazepam. Now, within complex structures such as this, it's sometimes useful to be able to refer just specifically to the aromatic ring within the molecule as a whole. So in other words, when you're describing this molecule in words, you might want to be able to refer someone specifically to just the aromatic group here or here. And so we have terms that we can use to describe aromatic groups. So if you have a complex molecule, I represent the complex molecule, the zigzag line there, squiggly line. And within that, there's an aromatic group. If you want to draw the reader's attention just to the aromatic group, we refer to that group by itself within a bigger, broader, more complex structure as an aryl group, A-R-Y-L, or alternatively and synonymously, a phenyl group, P-H-E-N-Y-L. And the YL suffix there, if we think back to our IUPAC nomenclature, is a bit familiar because we previously referred to alkyl groups such as methyl, ethyl, propyl as branches coming off of a parent chain. Similarly here, we're considering this to be a branch coming off of the broader molecule in the case of these complex structures. And so we refer to it as an aryl group or phenyl group if we're trying to refer and draw attention specifically to just this part of the molecule. Now, in the next video, what we will do is focus on how we go about naming introductory aromatic molecules, and we'll expand the scope of aromatic molecules to include some structures beyond just benzene.